All right, here we are. So we're back on Mark Renault's Calculus Atlas webpage. Good old Mark Renault. There's this one on here, number 17 here, that I want to start with today. The intuitive notion of the chain rule. So I have it open right here. And you guys remember I sent you a link to this page, so you can come check this out yourself. This is, here we have three variables, x, u, and y. All right, so what we're going to be talking about is composition of functions. Remember when we introduced that u variable in between? So we have an x, u, and a y variable represented by wheels here in this thing. So the x changing at a certain rate, right? And we can kind of change the rate of the x, and we can make it go faster, or we can make it go slower, or whatever. We can kind of adjust the speed of the x wheel up here, okay? Now, what we're going to do is we're going to connect the x wheel and the u wheel together. We can pretend that this is like a belt connecting two wheels, so the friction between the wheel and the belt is causing the belt to spin around, and the movement, the spinning of the x wheel is therefore causing the spinning of the u wheel. This is like an analogy for how one variable can depend on another via a function. Okay, so the more abstract idea here is that u would equal some function of x. So u depends on x. Okay, and then of course we want to ask about the rate of change. Okay, we want to ask about the rate of change of u relative to x. Now, there's a nice explanation of it down here. If you would scroll down and take a look here. What is the rate of change of u relative to the rate of change of x? Does u change twice as much as x? If you increase x a little bit, does u increase 10 times that amount, or just half that amount, or some other thing? Maybe as x increases, u decreases. That would be a negative rate of change. So the notation for that is this derivative notation. Du over dx denotes the rate of change in u relative to the rate of change in x. Okay. So right here, we can see that it tells us here that is 4. So what that means is that for every one time the x wheel goes around, the u wheel is going around 4 times. In other words, u is like increasing 4 times as fast as x. And you can see down at the bottom, actually, there's like a little it's sort of like every lap around the circle, x ticks up by 1. And so you can really look at these numbers and you can see this is moving that fast. Like that, not pretty slow. Like that. And then we see u is, 1, 2, 3, 4. I mean, you could think about it like musically, almost like a rhythm. Like it's 4, this is 4 to 1 ratio, right? So that is our representation of the derivative, right? The rate of change in u with respect to x. Now, the idea of the chain rule is when you have a chain of dependence. So now we're going to bring in the y variable and we're going to connect the u wheel and the y wheel. So now the change in u is causing a change in y, right? So now y is a function of u, and this is like a composition of functions where x determines u, which in turn determines y. Okay, so now we can ask the same question about the rate of change in y relative to u, or with respect to is another phrase you'll hear here. Change in y with respect to u is like the sort of It's the ratio of how much y changes for every one change in u. We can see that it actually takes 2 increases in the u to cause a single increase in y, right? So what that means is for every increase in u, the y wheel only goes around half a time, right? U wheel once around corresponds to only half of a turn of the y wheel. And that means the derivative of y with respect to u is 1/2. Okay. And now we get to the chain rule itself, which is the rule that explains how the y and the x are related to each other when we have a composition of functions or a chain of dependence like this. So the question now is, looking at y and x, what is the rate of change in y with respect to x? See if you can answer that question. Can you tell by looking? Yeah. It appears to be about 2. 1, 2. They're actually quite nicely aligned. 1, 2. They both kind of reach about 12 o'clock on the wheel at about the same time, but it takes the y wheel twice as long, or it takes the x wheel twice as long to get there, right? So the y wheel goes around twice for every one time. So then I can click reveal dy over dx, and indeed it is 2. Okay, if I change, and we notice, okay, and we should note before we move on that 4 times 1/2 does equal 2. If I change things, let's change, like here, the size of this x wheel, that changes the rate of change between the x and the u. Now it's 3. The y to u relationship is still the same, that's still 1/2, but now our rate of change here is 1.5, 3 times 1/2. I can make u bigger, or y, can change y to be whatever. Now this is a rate of change of 1 because they're exactly the same size. 0.75 times 1 is 0.75. You can do all kinds of fun things here. 2 and 0.3 multiplied together, 0.6. So what we recognize is no matter what relationship we have between x and u, and no matter what relationship we have between u and y, the relationship between x and y is always just the product multiplying together these 2 rates of change to give us the overall rate of change. That is the heart of the chain rule right there. It's this times this equals this. Okay. So in notation, it looks like this: dy over dx, the rate of change in y with respect to x, is the rate of change in y with respect to u, first of all, multiplied by the rate of change in u with respect to x. That is the chain rule. Okay, so let's go ahead and put that aside now. We'll pull up our our whiteboard. That's Calc2. Okay. When y equals f of g of x, a composition, y equals f of u, where u equals g of x, And the derivative of y with respect to x is the derivative of y with respect to u multiplied by the derivative of u with respect to x. Or in other words, the derivative with respect to x of y is going to be f prime of u, derivative of f with respect to u, times g prime of x. Or in other words, let me give myself a bit more space. The derivative of a composition, f of g of x, is f prime of, and then instead of writing the u inside there, I could have written g of x, and then times g prime of x. And these are all different representations of the chain rule, just using slightly different notation. Okay, so we can sort of compare them. This one is nice because it's with the Leibniz notation, the d blank over d blank, like the Leibniz dy over dx. It's very clear what the derivative is with respect to, right? So like the first one on the left there is the derivative of y with respect to x. And then on the right side of the equation, the first thing we have is the derivative of y with respect to u. It's very important in the chain rule to keep a distinction between these two things, the derivative of y with respect to x versus the derivative of y with respect to u. Those are different things. We need to be careful with them. Let's look at an example. Let's say you take the function y equals sine of x squared. This is a composition of functions. We could say this is f of g of x, where f of u is what you get when you take the inner function and you replace it by a u, right? So that would be sine of u. F of u equals sine of u. And u equals g of x, which is x squared. Okay. So if we ask what is the derivative of y with respect to u, it's the same as asking what's f prime of u. That's the derivative of sine of u here. That's cosine of u. And then if we ask what's the derivative of u with respect to x, that's the same as g prime of x. That's the derivative of x squared, which is 2x. And now what we do, we apply the chain rule. We say, then by the chain rule, the derivative of y with respect to x is going to be the derivative of y with respect to u, which is cosine of u, multiplied by the derivative of u with respect to x, which is 2x. Like that, cosine of u times 2x. But we don't want to actually leave our answer with a u in it. So the u substitution we're doing here is a nice, like, temporary sort of placeholder, you know, to kind of like simplify everything. But we don't want it in our final answer. So what we want to do here is go back and say, well, u is equal to x squared, right? So we'll do cosine of x squared times 2x. And there's our derivative, right? That's the derivative of this function. Cosine of x squared times 2x. So another example. Do one more example. Let's say like y equals, how about sine squared x? It's very similar, but now this is backwards. This is like sine of x and then that whole function squared. So now if I consider this as f of g of x, that would be where f of u is actually the squaring function u squared, and g of x is sine of x. Okay, I can get my derivatives here. F prime of u is this time 2u. G prime of x is cosine of x. And what I get is y, the derivative of y with respect to x is f prime of g of x. So I got to do f prime of g times g prime. And I get 2u, right? I can just write it this way, 2u times cosine of x. But then I make sure to put my u equals g of x, my u equals sine of x back in again. So 2 times sine x times cosine x. Okay, time for you guys to try. Your turn. Let's head over to the Jamboard. Okay, so start by going over to D2L. Okay, on the D2L page, Jamboards are right here. You click on the Jamboard. Here's the Jamboard. We'll go ahead and clear this up. Oh, it's already clear. Nice. And I will put some problems on here. So let's do y equals tangent of 4x plus 2. And then we'll do e to the power x plus x cubed, and cosine of e to the power x, sure, and the square root of 4x plus 9, and secant of square root of x. Oh, and then let's do one more spicy one because some of you like it spicy. Let's do sine to the power 3 of, so sine cubed of e to the power 5x plus 1. Spicy. Okay, let's go ahead and distribute yourselves across these pages and work on whichever one you appeals to you. I'm going to stop sharing my screen for a little while, and I'll just kind of watch. You guys are free during this work time to ask questions of me or of one another. You can use the Zoom chat to ask questions, and if you want, I can also open a like a breakout room to like talk to people individually. If you want to ask a question more like quietly, I guess, without everybody listening in. That's available as well. So let you guys go ahead and get to work. What's FO mean? All right. I'd prefer we don't have jokes going on. So guys, this is supposed to be a learning environment. And so, you know, we can't do this. We can't have nice things if you guys aren't gonna like respect the environment. Okay. So, all right. Okay, we're back to recording and I'll share my screen. All right, and we're going over the problems we started working on earlier. So I was just about to say a comment on page 4 here. So, oh, hey Adam, just wanting to let you know that you're not muted right now. So if you're chatting, we can all hear you. Yeah. Okay, so let's see. So right here we have the derivative of the outer function, as I call it. I like to think of like the f here. Oh, let's do it in like blue. This is like our outer function because it's on the outside. It's the square root that's outside the everything else. And then this is our inner function. So just introducing that vocabulary, outer and inner. Okay, that's not like standard vocabulary. It's more so just what I call it, I think. Pretty common though. And then, so here's the derivative of the outer function. That's looking good. Here is the derivative of the inner function. That's looking good. But then there's a problem when we put the pieces back together again. Can anyone recognize the problem?
It's missing the 4x plus 9.
Sorry, what's that, Julia?
It's missing the 4x plus 9. It should be 4x plus 9 instead of 4 but inside.
Correct. Perfect. Yes. So if I write out the way it looks, it's f prime of u times g prime of x, but u was equal to the original g of x. So where are the primes? The primes are only here. Oops. Let's make that a little clearer. Here and here. What's inside f prime is just the original g of x, not the derivative. So let's fix this up down here, right inside here, inside of this like -1/2 power function here. Oops. Is that me? Oh, no. That should be our original g of x, 4x plus 9. I got it for you here. Yeah. So, yeah, that was the only mistake there. And now we can call that one good too. So, going well. All right. So any questions, or are there any of these you want me to go over, or is there anything, any sort of particular example you want to see?
Tristan, on the one that you were just doing, can we cancel the 1/2 and 4, like 2 to 4?
Oh, sure. Yeah, you certainly can reduce fractions or just do any other simplifying. I guess in this case, the only simplifying I would say you can do is like, yeah, canceling a 2 factor. So 1/2 times 4 is just 2. You can, if you want, move that negative power function down to the denominator and make it positive. If you don't like having negative powers, you can write it in the denominator. But all that stuff is kind of optional for now. There's no particular need to do any simplifying after you've got your derivative at this stage. Nice work on this spicy one. This is really spicy because this is a composition of like 1, 2, 3, 4 different functions. So this requires like a bunch of substitutions. So it looks like we're using u, and then u equals g of w, and then w is h of t, and t is j of x. So I really kind of threw you off the deep end here. But great job to whoever was working on this. This is how you handle it when there is more than one composition involved. So one composition would mean two functions, right? F and g, f of g of x. So one function stuck inside of another. But if you have more than just those two layers, there's multiple compositions. And so it's like you're kind of repeating the chain rule. You're chaining the chain rule, which is kind of a funny way to say it. You're chaining the chain rule together. And so you have like derivative of the outermost function with the inner function stuck inside, and then times the derivative of the next function layer in with the original still in there, and then times the derivative of the next layer in, and then finally times the derivative of the innermost layer. It's like, yeah. So maybe I can come over here to the main whiteboard and just show you what that looks like. Chaining the chain rule. So if you have y equals f of g of h of x, then we can say, you know, this is f of u equals g of w, and w equals h of x. So then dy over dx is dy over du times du over dw times dw over dx. This is with three functions, two compositions. So then what it looks like is f prime. I'm going to highlight the derivatives in like a red here. I got f prime. Oops. Hey, Luca. Hey, hang on. Okay, sorry about that. That was the 2-year-old or 1-year-old just walking in. He's almost 2. He'll be 2 in a month. There's that. And then we have like a times g prime of h of x. And then we have times h prime of x, I guess. So yeah, so that's what it looks like when you're chaining multiple things together. Quick example of that, similar to the one I put on the other page. Let's do something like tangent of 3x plus 2 squared or something, right? The derivative of that, if that's y, or y prime here, is going to be like derivative of tangent, which is secant squared. Let's do it in red.
Oh.
Secant squared. All that stuff is still in there. 3x plus 2 squared. And then you multiply by the derivative of the squaring function, which is 2 times that stuff to the power 1, with the 3x plus 2 still in there. And then finally you multiply by the derivative of 3x plus 2, which is just 3. I don't need the power 1. I'm going to get rid of that power 1 because I feel like it looks like a prime, and it's not meant to be a prime. It's meant to be a 1. Okay, so I think that's pretty clear. That's what it looks like when you chain them together. So, okay. So do you folks have any other, questions? Oh, we're at the end of our time. I'll take a question or two if you have it, though.
I did.
We've introduced this today, but you guys can practice over the weekend. You guys have an exercise set due tonight. It doesn't have any chain rule on it. But I'll be looking at that as soon as I can and getting you your feedback. All right. If you haven't already, check out the feedback I gave you on the last exercise set. That's all done and graded. So, you can take a look, and I'll be available in office hours today if you have any questions. Bye, everyone.